Hello, welcome to another module in this massive open online course. So we are looking at frequency shift keying, alright, and in frequency shift keying, well, we are considering two different waveforms to represent the information bit 0 and 1, which are shifted in frequency, correct. So we are considering two different frequencies, f1 and f2. Since the waveforms are shifted versions of each other in frequency, this is known as frequency shift keying, alright. And what we have seen in this is that my yt corresponding to 0 is a times p1t plus nt, that is, this is for information bit 0. For 1 we have yt equals a times p2t plus nt. We have seen the matched filter, optimal receive filter, optimal receive filter is ht equals p1, well, t minus t minus p2 t minus p2 t minus t. Okay, so this is the optimal receive filter. Optimal receive filter, in the sense, you must be well familiar by now. Optimal in the sense, this maximizes the output SNR, or signal to noise power ratio. Okay. Now consider the transmission of information bit 0. Consider information bit 0. We have for this yt equals a times p1t plus nt. Now matched filter or receive filter with ht, ht equals p1t minus t minus p2t minus t, followed by sampling at t equal to t. Now that gives us, if you can look at it, we have r of t equals, well, integral minus infinity to infinity y of y of tau times h t minus tau d tau. Substituting for h of t, this gives us integral, this gives us integral minus infinity to infinity. Y of t is basically your well, this is a p1 times p1 of tau, a p1 of tau, of course there is noise also, okay, a p1 of tau plus n tau times the filter h t capital T minus tau p1, which is, you can see, is simply p1 tau minus p2 tau d tau, and that gives us, well, that can be split naturally into two terms, A P1 tau into P1 tau minus P2 tau d tau. This is your signal component, plus integral minus infinity to infinity n tau P1 tau minus P2 tau d tau, and this is your noise component. So, corresponding to the transmission of information, the signal, the waveform corresponding to information bit 0, we have computed what is the output after filtering with h t followed by sampling at t equal to capital T, where capital T is the symbol duration. These are the signal component and the noise component. Now, let us simplify both these components individually. Okay. Now, let us come to the signal component. Now, the signal equals minus infinity to infinity A times P1 tau into P1 tau minus P2 tau d tau, which is equal to integral minus infinity to infinity A times P1 square tau d tau minus A times integral minus infinity to infinity P1 tau P2 tau d tau. Now, you can see this is nothing but the energy of the pulse, this is equal to 1, and this integral minus infinity to infinity P1 tau P2 tau d tau, we have seen this is the inner product of P1 tau comma P2 tau, which is equal to 0. So, this inner product is 0 because P1 tau and P2 tau we have said are orthonormal basis functions of the signal space. So, therefore, all that is left is A times EP, substituting EP equal to 1, this is A. This is, remember, the signal component after matched filtering. Now, if you look at the noise component n tilde, which is equal to minus infinity to infinity n tau P1 tau minus P2 tau d tau. Now, this noise we have previously seen from our analysis of the noise output at the noise at the output of a matched filter. We have said that the input noise is a Gaussian noise process, the output noise process also Gaussian. Once you sample it, you get a Gaussian random variable. If the input noise process is 0 mean, the output noise process is also 0 mean. Okay. So, n tilde is Gaussian, mean equal to 0. Now, the variance is eta naught by 2, and this also we have seen integral minus infinity to infinity magnitude h tau square d tau or h t minus tau square d tau, which is equal to n naught by 2 integral minus infinity to infinity, well, P1 tau, or let me write it for the sake of just being clear, let me write this as T minus P1 tau minus P2 tau square d tau. Now, this is, now expand this P1 tau minus P2 tau whole square, what you have is P1 square tau plus P2 square tau minus twice P1 tau P2 tau d tau. Now, you split this into two terms or split this into rather three terms. This is equal to n naught by 2 integral minus infinity to infinity P1 square t minus tau d tau plus n naught by 2 integral minus infinity to infinity P2 square not t minus tau P2 square tau d tau plus the third term which is n naught by 2 integral minus infinity to infinity P1 tau P2 tau d tau. And now, you can see once again this is integral minus infinity to infinity P1 square tau d tau, that is EP, the energy of the pulse, which is 1 integral minus infinity to infinity P2 square tau d tau, this is also EP, which is equal to 1. This is once again, this is the inner product between P1 and P2, which is equal to 0. So, what is remaining is basically, if you can see the noise power or the noise variance, that is n naught by 2 plus n naught by 2, we are setting EP equal to 1 plus 0, which is equal to n naught by 2 plus n naught, which is equal to. So, this is the noise power at the output after sampling. Okay. So, this is the noise power. Previously, we had always noise power n naught by 2, but now we have noise power after sampling equals n naught. So, observe that this is basically once again slightly different with respect to what we had for amplitude shift keying and also binary phase shift keying, where the noise power after match filtering and sampling was n naught by 2. Now, we have noise power n naught. Okay. So, basically the output is RT equals, well, A EP plus n tilde, setting EP equal to 1, this is A times, writing EP again because it is, so that the expression is general and can be valid also for scenarios where EP is not necessarily equal to 1, n tilde, this is Gaussian with mean equal to 0 and variance is equal to n naught. Now, similarly, corresponding to the transmission of information bit corresponding to bit 1, well, corresponding to bit 1 we have yt equals A times P2t plus nt. Now, when we matched filter this or receive filter this, with once again h of t equals P1 t minus t minus P2 t minus t, the output will be, well, you can verify this, RT is minus AEP plus n tilde, again setting equal to 1, this is equal to minus AEP or minus simply A minus A plus n tilde, where n tilde is Gaussian. Once again it is the same thing, the mean equals 0, variance is equal to n naught. Therefore, now if you look at this scheme comprehensively, I can summarize this as the output after filtering and sampling is basically given as corresponding to 0 and 1. This is A plus n tilde, this is minus A plus n tilde. Okay. Now, you can see this is similar to BPSK. This model, if you can observe closely, model is similar to BPSK, that is binary phase shifting, except noise variance is sigma square equals n naught, not n naught by 2, right. In BPSK, the noise variance what we had computed n tilde, that is the noise variance after filtering and sampling, was n naught by 2. Okay, here it is n naught. Therefore, now the threshold, again by symmetry, look at it, the mean is shifted for 0, the mean is shifted to A, for 1 the mean is shifted to minus A. Symmetry, by symmetry again, the optimal detection rule is to compare the sample RT with 0. So, once again by symmetry, the optimal decision rule is once again, that is your RT greater than equal to 0 implies decide A naught equals 0, that is, this is the information bit. On the other hand, if RT is less than 0, that implies decide A naught is equal to 1. So, therefore, that summarizes your decision rule. This is the optimal decision rule, or FSK. It is not very different from that, or in fact, very similar to that of BSK. This is the optimal, in fact, we can say threshold based decision rule for frequency shift keying, FSK. For frequency shift keying, that is frequency shift keying, FSK. Okay. And the corresponding bit error rate, again we can see corresponding bit error rate, that is, if you look at this bit error rate, which is either, which is again another thing that you should be very familiar with by now. This is the bit error rate, bit error probability, or this is known by many terms, or the probability this is equal to Q times A divided by sigma, which is equal to Q times A divided by square root of n naught, which is equal to Q times A square divided by n naught. Now, substitute A equal to EB, substitute A equal to square root of EB rather, where EB, as we have seen before, equals the energy per bit. So, bit error, this becomes Q square root of EB over N naught. This you can say is the probability of bit error or bit error rate. So, this is the bit error rate for frequency shift key. Let us note that. This is the bit error rate for frequency shift key, that is FSK. Okay. So, this is the bit error rate for frequency shift keying, and again you can see if you compare it with bit error rate. Now, bit error rate for, now if you look at bit error rate for BPSK, that is basically Q square root 2 EB over N naught, and bit error rate for both amplitude shift keying comma frequency shift keying is Q square root EB over N naught. And if you remember our discussion, our previous discussion, the Q function is the tail probability of a Gaussian random, of the standard Gaussian random variable. Therefore, the Q function is decreasing in its argument, and therefore, this implies that the bit error rate of both frequency shift keying and amplitude shift keying for an average bit energy of EB is lower. The bit error rate is higher, the bit error rate performance is worse, because remember the Q function is decreasing. Therefore, Q of square root of 2 EB by N naught is less than Q of square root EB over N naught. Okay. So, the bit error rate of both amplitude shift keying and frequency shift keying is higher. And how much and how inefficient are amplitude shift keying and frequency shift keying in comparison to binary phase shift keying? We have seen previously that they are 3 dB worse in comparison to binary phase shift keying. The reason being, you need twice the average bit energy, that is, you need twice the average bit energy EB to achieve the same bit error rate performance in amplitude shift keying and frequency shift keying as that of BPSK. Okay. So, let us also note that once again, although that should be plenty clear. So, the first point is BR of ASK is identical to that of FSK. Obviously, the comparison has to be fair for equal average energy per bit EB. Further, the BR of ASK comma FSK is greater than BR of BPSK. This is because remember Q function is decreasing in its argument. The Gaussian tail probability is a monotonically decreasing function. And more importantly, we also have the fact that how inefficient are they. ASK comma FSK, amplitude shift keying and frequency shift keying, are 3 dB inefficient or 3 dB worse which basically means for same bit error rate, to achieve the same bit error rate, your ASK amplitude shift keying slash frequency shift keying need three dB, they need 3 dB more power. So, they are basically 3 dB to 3 dB worse, amplitude shift keying and frequency shift keying are 3 dB worse than binary phase shift keying. So, basically you can say binary phase shift keying for the same average energy per bit EB achieves the lowest bit error rate amongst BPSK, ASK and frequency shift keying. Alright, so BPSK is the amongst these three, BPSK binary phase shift keying is the most efficient modulation scheme, and the reason for that, if you explore it, will be because binary phase shift keying for the same average bit energy uses antipodal signaling, that is, it uses signals plus A and minus A, alright, which maximizes the distance between the constellation points. Okay, you can note this informally, although we have not shown this rigorously. It maximizes the distance between the constellation points for the same average bit energy EB, while both amplitude shift keying and frequency shift keying do not do this. Alright, so they have a poorer performance. So, the performance is poor in comparison to the binary phase shift keying, which we have shown to be a very efficient digital modulation scheme. Okay. So, that completes our discussion on frequency shift keying based on this framework, remember, of the signal space, the concept of signal space, where we are now employing not one but two pulse waveforms which are both of unit energy, normalized unit energy, alright, and are also orthogonal to each other. So, they constitute an orthonormal basis for this signal space. We are representing the information bit 0 using A times P1t, that is along the signal P1t, basis function P1t. We are representing the information bit 1 by A times P2t, which is along the direction in the signal space, or which is along the basis function P2t, and therefore, we are now using a two dimensional signal space in frequency shift keying. That is the interesting aspect about frequency shift keying. Alright, so we will stop here.